Hey, Algebra 2 honor students, this is going to be some more functions here. We're still in Unit 2. We're on day 11, which is all going to be about piecewise functions. We are going to be taking some notes by hand today. You might want to do them on graph paper since we're doing a lot of graphing associated with piecewise functions. Essentially, what a piecewise function is it's graphing a function over a restricted domain, over a restricted interval of x values. So to get the conversation started, we're going to start by looking at a classic function that we know a lot about, f of x equals x squared. It's that parent quadratic function. But I only want to sketch this for x values that are less than 2. And I think what makes the most sense is to think about this by making a table of values. Where since I want x values to be less than 2, let's kind of like jump back a ways from x equals 2. Maybe I'll jump all the way back to like x equals negative 2. And just to kind of see what this looks like, I'm going to make a quick table of values by plugging these inputs, these x values, into my function, finding the y values, and then we'll plot them as points. Well, negative 2 squared I know is 4. Negative 1 squared is 1. 0 squared 0. 1 squared is 1. 2 squared is 4. Okay. Now that last point, we're going to have to talk about that in a second. Because remember, I only wanted to sketch this when x was less than 2. So that should mean something to us when we go to make our sketch. But when I come over here and create a set of axes, I know at negative 2, 1, 2, 3, 4 that works. And negative 1, 1, and 0, 0, 1, 1. But then that last point, 2, 4, what we're going to have to do there is put an open circle. Because I want to graph this for x values that are less than 2, not less than or equal to 2. So at the point 2, 4, go ahead and put an open circle on the graph. And students sometimes misinterpret this to mean that, oh, the last point we should have plotted then is at 1, 1, right? If x has to be smaller than 2, then why don't I just stop at 1, 1? Well, what about when x is 1.1, 1.2, 1.3, 1.99? You know, if x is 1.99, that's less than 2. I better plot a value there. So we really have to make sure we include all the values that are even non-integer, right, when we make our sketch. So we're going to connect those backwards a little bit. And by the way, you know, I didn't have to stop my table at negative 2. I could have gone and plugged in negative 3 and gotten 9 for the output. So when you continue this graph on the left side here, please make sure you indicate that there be an arrow indicating that any x value less than 2, we'd have this graph defined. But as soon as I get to x equals 2, we have to stop at an open circle. And that's just graphing a piece of the graph y equals x squared. But if we're unsure how to visualize that, I think this table of values really is going to help us in a lot of instances. So let's take a look at another example. Typically, when you see piecewise functions defined, you're going to see this little curly bracket to define them, kind of like this. And this might even look familiar from Algebra 1 because I know you learn about piecewise functions in Algebra 1. So if this sounds familiar or looks familiar, that's why. So we've got the function x plus 1. When x is less than or equal to, we'll say negative 1. And then we're going to graph 3 minus x when x is greater than negative 1. Okay. So the first thing I'm doing when I'm looking at these two functions here that we're going to graph pieces of is that knowing in my head that they're both linear. Right? They're both of the form y equals mx plus b, but we're going to graph the one on top when x is to the left of negative 1, and then the one on the bottom when x is to the right side of negative 1. So if you can't visualize what this looks like, let's go ahead and make a table of values. I'll start with f of x equals x plus 1. And my table of values have to be less than or equal to negative 1. So maybe I'll jump back as far as like negative 4. It's really as far as you have to go to get the pattern of how to sketch this. Now, since we know it's a line, it shouldn't get us, it shouldn't take us too long to figure out what's happening here. But negative 4 plus 1 is going to be negative 3. Negative 3 plus 1 is negative 2. Negative 2 plus 1 is negative 1. This is going to be 0, right? Just plugging in those values to this function. And that last point of the interval, when x equals negative 1, what do I have to do there? We're going to put a closed filled-in circle. Because in this instance, x can equal negative 1 for this linear part. So we want to make sure we fill that in. All right, let's talk about f of x equals 3 minus x. So now I want to pick values of x that are greater than -1. Notice how I'm still going to start by plugging in -1, but then maybe I'll plug in 0, 1, and 2. So 3 minus a -1 is +4. Just be careful with that. 3 minus 0 is 3. 3 minus 1 is 2. 3 minus 2 is 1. And at that initial point, x equals -1, what do I have to make sure of? For the function 3 minus x, this has to be an open circle. Right? X can't be equal to -1 for this function, but I want to make sure I know kind of what this line is approaching the closer we get to x equals -1. So based on my x and y values list that we've determined here, I would say we're pretty good if we draw our axes kind of straight up and down through the middle here. Okay, sometimes I like to offset my axes, like, even in this parabola up here, I knew I wouldn't have any negative y values. So use that logic to your advantage when needed. But if I start with the first part, -4, -3, and then it's going to have a slope of 1, so we can kind of cheat a little bit and use that slope of 1. But make sure as soon as you get to -1, 0, you stop. You can put a closed circle there. And then we're going to continue to the left in that direction forever and ever and ever. All right, what happens when we plugged in -1 for the next function? -1 for the next function, the output is 4. Okay, but make sure you put an open circle at -1, 4. I kind of made a big deal about it there. But then 0, 3, and then we're now going to have a slope of -1 after we get through x equals -1, right? So we're going to get a graph that looks something like this. And that is exactly what this graph would look like. So I'm going to ask you a quick question. For what values is f of x discontinuous? Okay, when we think about where graphs are continuous or discontinuous, it's basically, can I draw my graph without picking up my pen or pencil? And it's pretty clear in this example that I can't draw my graph without picking up my pencil at x equals -1. So when I say for what values, I'm actually really talking specifically about x values here. For what values of x is f of x discontinuous, and it happens to be right at this jump at x equals -1. Okay. Did that have to be the case? Not necessarily. Right? We could have easily defined a linear function with a negative slope that picked up where I left off. We could have determined that. But in this instance, there's definitely that big jump at x equals -1, so we say that that's a point, a value of x for which this function is discontinuous. All right, let's go ahead and try another example. So we'll call this example 3 here. I'm going to make 3 parts for this one. F of x equals the absolute value of x plus 4 minus 1 when x is less than 0. Then I'm going to do x squared plus 1, so we'll do a quadratic in the middle. When x is between 0 and 2, notice I put less than or equal to for both of those, right? Those symbols will be important. And then finally, we'll choose f of x equals 5 when x is greater than 2. So in this instance, you're really going to need 3 tables, right? We got one for the absolute value function, one for the quadratic, and the last function of f of x equals 5. I like to call that a constant function. Okay, so we need values that are less than 0 for this one. Maybe I'll go back to like -4, -3, -2, -1, 0. Okay, when I plug in -4, -4 plus 4 is 0. Absolute value of 0 is still 0, minus 1 is -1. Just be careful with absolute value, right? If you have a negative inside here, the absolute value of a negative is a positive. I don't think that will really affect these next values, right? Absolute value of this would be -3 plus 4, which is 1. Absolute value of 1 is still 1, minus 1 is 0. And just if you plug in the rest of these, you're going to find that these start increasing by 1 each time. So it's going to be 1, 2, and finally 3. At that last point, 0, 3, what do we have to consider? Well, x is only being graphed less than 0 here. So that's definitely going to be an open circle. All All right, so what am I going to choose for the next table for x squared plus 1? Let's choose everything from 0 to 2, right? I mean, there's not that many integers to choose there. It's just 0, 1, and 2. I think it makes sense to choose all of those to plug in. 0 squared plus 1 is 1. 1 squared plus 1 is 2. 2 squared is 4, plus 1 is 5. I'm going to box in both of those and say that those are the endpoints of this interval. And since each of those endpoints should be included, right, they're each less than or equal to, you should have closed circles in both of those locations. Finally, for the last part of our graph, we're graphing f of x equals 5 for x values bigger than 2. So even though it says bigger than 2, just like we've seen in the other examples, start at 2 and then increase from there. The really nice thing about having a constant function, f of x equals 5, is no matter what the input is, the output is 5, 5, 5, 5, 5. Okay, and that initial point should be open. Now, really quickly, I don't know if you've caught on to this, but if you have, the last graphs ended on a closed circle at 2, 5. This graph says it should be an open circle at 2, 5. So what's going to happen there at the point 2, 5? Well, you know what? I'll let you find out in 1 sec. I'm going to go ahead and start sketching this here. All right, so here's my graph. So I'm going to start with the absolute value part, which is -4, -1, and -3, 0. We've got -2, 1, -1, 2, and 0, 3 has to be open, like that. All right, you have to be cautious about this. I kind of did this on purpose. See how the last point I picked was at -4, -1? Students very commonly want to just keep going. And they're like, oh, yep, this must be a line that goes on forever and ever. But don't we know absolute value looks like a V? And where should the bottom of this V occur? Isn't it at -4, -1? So even though I didn't go back far enough in my table to figure that out, you have to have the knowledge that this goes back up after hitting that vertex. So please make sure you're careful with that, sometimes we don't go far back enough in the table to see that turning point right there. But you have to have the knowledge of, wait, this should look like a V. Am I going to be seeing that point of the V, that vertex? And in this case, we will. All right, let's jump down to the next part. This is going to be a parabola that got moved up 1 unit. So we've got 0, 1 that should be closed, 1, 2, and then 2, 5, 3, 4, 5, which should be closed. So for the last part of this graph, that's what was in question over here. Wait, but then I'm supposed to put an open circle at 2, 5. Okay, here's what you're not going to do. Don't put an open circle surrounding the closed circle. I mean, that's cute and all, but it's not right. All right, so try and avoid that. Just know that the closed circle overrides the open circle. So even though this should have been open according to this inequality, it's actually going to get filled in because 2, 5 is already filled in over here. So we can actually keep going at a constant rate of 5, okay, once we get up to that point. So if you have any questions about that, you'll let me know. I say we do one more just for good practice here, and then I'll let you try one that we'll go over the next day. So, oh, by the way, where was that discontinuous? Was this discontinuous anywhere? Because I want you to be able to answer that question as well. So this is discontinuous at, was it discontinuous at x equals 0? Yeah, definitely a jump at x equals 0. Was it discontinuous at x equals 2 where we had that other split? Nope, I don't have to pick up my pen at x equals 2, right? I go up the hill. Once I get to the top, I just keep walking on flat ground. So this is only discontinuous at that first location, x equals 0, but it's not discontinuous at x equals 2. All right, if you're feeling pretty good, by the way, you can hit pause at this point once I write down the next example, and you could try it. I guess this is number 4, if I'm going to number it correctly. So f of x equals x plus 2 squared minus 1 for x values less than or equal to 0. Let's throw in an exponential function, 2 to the x. For x values between 0 and 2, just make sure you're paying attention to the inequalities here. And then we've got a linear function for the last one, x minus 4. when x is greater than or equal to 2. Okay. So we've got a parabola, an exponential function, and then we've got a linear function. So if we're thinking about kind of what those pieces are all going to look like when graphed together, it's good to have an idea in your mind as to what we might be seeing. If I need values that are less than 0, maybe I'll jump back to like -3 here, get those 4 points. By the way, the turning point of this parabola here, because I know what that looks like, is at -2, -1. Which is going to be a point on my graph. There's the vertex right there. But then it's going to turn around and start heading back up on the other side. Let's fill in some of the other values. -3 plus 2 is -1. Squared is 1. But -1 is 0. And since this is on the other side of the turning point, this will be 0 as well. You can almost cheat a little bit. Or just be smart about it. 0 plus 2 is 2. Squared is 4. -1 is 3. Okay. So what's going on at 0, 3? Open or closed? We've got to have closed because it said less than or equal to 0. Okay. The function 2 to the x. And this is between 0 and 2. Okay, let's plug in all those. 0, 1, and 2. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. Okay, both of those endpoints need to be open, right? 0 and 2 are not included in this function at all. So you need to have open endpoints in those locations. Did these match, by the way, 0, 3 and 0, 1? Nope, so this doesn't get filled in. Okay, so we can kind of pay attention to that as well. All right, and then for the last part, x minus 4. We need to pick values of x that are greater than or equal to 2, like 2, 3, 4. I don't need that many. I know what a straight line looks like, right? But to know where the starting place is, 2 minus 4 is going to be -2. 3 minus 4 is -1, and then that's going to be 0. Okay, at the point 2, -2, we're going to have a closed circle because of the inequality there. Do those match? Nope. 2, 4, and 2, -2 are definitely different places. So in this instance, we're not going to have this closed circle fill in that open circle. And do I have room over here to fill in this graph? What do you think? Yeah, I think I could squeeze it in. We'll give it a shot. Okay. So we'll do this. I'm going to plot, if I went all the way over here, -3, 0, -2, -1, -1, 0, and then 0, 3, which is closed. Okay. Now remember, when you're graphing this, we stopped at -3, 0, but your graph shouldn't. We could have plugged in -4 and -5 and -6. So please make sure you extend that graph all the way to the left. All right, then at 0, 1, we need an open circle right there. And then we've got 1, 2, and 2, 4. 1, 2, 3, 4. Make sure you have an open circle there as well. Okay, remember an exponential function is going to have that curve to it. Okay, so do your best, even though there's only 3 points here, to kind of bend through those. And lastly, we need to be at 2, -2 with a closed circle, 3, -1, 4, 0. And don't just stop there. Keep going forever and ever. And that's what the last part of your graph should look like. So if I were to ask you, is this graph discontinuous anywhere? The answer is yes. It's discontinuous at both the x values where we had jumps here at x equals 0 and also at x equals 2. Okay. So I think this is now a good time that if you didn't try that one on your own, try this one on your own. And we'll go over it tomorrow in class. So we're going to do absolute value of x plus 4 plus 2 when x is less than or equal to -2. Then we're just going to do x squared in the middle from -2 to +2. And then I want you to do absolute value of x minus 4 plus 2 when x is greater than or equal to 2. Go ahead and make a sketch of this in your notes. And then once you're done, go ahead and tell me, is it discontinuous anywhere? And really the only issues that we're going to wind up having are maybe at x equals -2 and maybe at x equals +2. Because by themselves, these are all continuous functions. Okay? All right. We'll catch up on this tomorrow and then just do a little bit more piecewise before we wrap up Unit 2 on functions.